Hey everybody. Today we're getting into infinite series. An infinite series is just a sum that goes on forever. For example, 1 plus a half plus a quarter plus an eighth and so on. Usually we write these with summation notation, so sigma k equals 0 to infinity, 1 over 2 to the k. The way we deal with that is we plug in 0 into that formula, then plug in 1, then plug in 2, and so on, and just add up all the results. A couple more examples. The sum of the square numbers, 1 plus 4 plus 9 plus 16. And here's another one, sum j equals 1 to infinity, 3 times 10 to the negative j. That's 0.3 plus 0.03 plus 0.003 and so on. We can write that last one in a slightly more compact manner, 0.3 with that bar over it, 0.3 repeating, also known as 1/3. Tiny bit of notation. A lot of times we'll write sigma a sub k, where ak is just going to be the kth summand in that series. So we'll do that when we want to be as general as possible. All right, so whenever you have a series, you also get a sequence to go with it, namely a sequence of partial sums. So Sn, the nth partial sum, is going to be what you get when you add up the first n elements of the series. For example, looking back at that first series that we had on the previous slide, sum k equals 0 to infinity, 1 over 2 to the k. S1, the first partial sum, is just going to be 1, the first element of that sum. S2 is going to be the sum of the first two, so 1 plus a half. S3 is going to be the sum of the first three, 1 plus a half plus a quarter, and so on down the line. Now, we know how to talk about convergence of sequences. We've already covered that. We're going to say that a series converges if that sequence of partial sums converges. And we're going to say that the series diverges if the sequence of partial sums diverges. Perhaps the single most important example of a divergent series is the harmonic series. This is just the sum of the reciprocals of all the positive integers. 1 plus a half plus a third plus a fourth, and so on. If you keep adding up elements of this series, you can get as big a number as you like. It happens slowly, but you will eventually get to as big a number as you like. Let's briefly see why that's the case. We're going to look at the partial sums that correspond to the powers of 2. So S2, S4, S8, S16, etc. So of course S2 is 1 plus a half, 1 and a half. S4 is S2 plus 2 more elements, 1/3 and a fourth. Each of those new elements are bigger than a fourth, and so in total the new elements are bigger than half. So S4 is going to be greater than 2. So if you compare S2 and S4, we've gone up by more than 1/2. When we do S8, we're adding in 4 new elements, each of which is bigger than the smallest of those 4, bigger than an eighth. So S8 is going to be bigger than S4 plus 4 times 1/8. So we're adding in another half. We're greater than 2.5. We can do this again for S16 and get that we're going to be greater than 3. And S sub 32 is going to be greater than 3.5, and so on. So by going far enough, we can make the partial sums bigger than any number we like. It happens slowly, but it happens. Probably the most important example of a convergent series is the geometric series, AR to the k, which converges when r is between -1 and 1. Here a is representing the first element of the series, and r is the ratio between adjacent summands. So to get from one term to the next, you multiply by r. So the series looks like a, ar, ar squared, ar cubed, and so on. Let's see why this converges when r is between -1 and 1. Here's a formula for s sub n, adding up the first n elements of the series. And then let's multiply everything by r. And that essentially just shifts us over because this is a geometric series where the ratio between the terms is always r. Now if I subtract, I'm going to get a lot of cancellation. Take Sn minus Rsn, and you just get a minus ar to the n plus 1. And I can solve that for Sn. Sn is a times 1 minus r to the n plus 1 all over 1 minus r. Of course, we're interested in the limit as n goes to infinity of that sequence of partial sums. Now, as n goes to infinity, r to the n plus 1 will go to infinity if r is bigger than 1. And it'll keep alternating back and forth getting bigger and bigger when r is less than -1. So the r to the n plus 1 only goes towards 0 if r is between -1 and 1. That's why convergence only happens for r in those regions, for r in that interval. If r is between -1 and 1, then as n goes to infinity, the r to the n plus 1 goes to 0, and I'm just left with a over 1 minus r. This is a formula that comes up from time to time, and it's good to have this in your notes somewhere so that you can refer to it when you need it. It's very frequently not obvious whether a series converges or not. So as you look at the sum of 1 over n, the harmonic series, that's one that diverges as we saw. However, if you look at the sum of 1 over n squared, that one does converge, as we'll see in a future video. So there's a lot of techniques that we can use to determine whether a series converges or diverges. And we'll need to get into those in future videos. One rule to know right now is the test for divergence that basically says that if you have a convergent series, then the generic term an has to go to 0. To say it differently, if the generic term does not go to 0, then the sum of all the generic terms together, in other words, the series itself, is going to diverge. For instance, the sum of n over n plus 1, starting at n equals 1 or any other number, is going to diverge because as n goes to infinity, n over n plus 1 goes to 1. So because the generic term is not going to 0, the series cannot converge. One really important warning here. Even if the limit of the an's is 0, the series could diverge. You just don't know yet. And we've already seen one example of this, the harmonic series, 1 over n. As n gets larger and larger, this term, 1 over n, does go to 0, but the series does diverge. In a case like that, you've just got more work to do. Let's finish up with just a few important properties of convergent series. These are all going to correspond to properties of the summation. If you have two convergent series, a sub k and b sub k, then the sum of ak plus bk is the sum of ak plus the sum of bk. Similarly with the differences, and if you have a constant multiple here, c being a constant, you can just factor it out. Now, it's important to remember these operations are only true, and in fact they only make sense when you're talking about convergent series. If the series diverge, none of this makes any sense, and you shouldn't try and do any sort of algebra like this. One final warning, if you're trying to do the sum of a product or the sum of a quotient, there's not a simple rule for that. There's things you can do with it, with those formulas, but they are a lot more complicated. We're not going to really cover it in Calculus 2.